Okay, so hopefully you've watched the previous 3 videos on reaction rates and the reaction order numbers. And so now we're going to do some practice problems. Now, before we get into the practice problems, let's go ahead and just review really quickly the rate law, which is the rate equals K, and that K is called the rate constant. So rate constant. And this is different for each chemical formula. The rate constant is going to be different for each chemical formula. So some of these practice problems are going to be us figuring out what the rate constant is. And then the rate constant is times the concentration of A, or the concentration of any molecule. Of course, we're dealing with reactants, which are the ingredients. They are the the molecules on the left side of the yield arrow. If you're making a cake, the ingredients would be the flour and the sugar and the eggs, and the products would be the cake itself. So the reactants are like the ingredients when you're cooking. And then this n up here is the exponent of whatever order number this formula is going to be. And we went over how to find the order numbers in the previous videos. So if you don't know, go back and check in the previous videos how to find the orders. So in zero order, the formula for the rate is going to be K times the concentration of A. And by the way, when we're dealing with concentration, we put brackets around the element or the ion or the whatever chemical we're dealing with. If it's oxygen or carbon dioxide or anything, we put brackets around it, and that means that we're talking about the concentration of that chemical. And when we're talking about the concentration, this is the same thing as capital M, or molarity. And molarity is the numbers of moles in 1 liter of solution. So that's the concentration. And that's why there's brackets around the A in here, because we're dealing with the concentration or the molarity of that element. Now, also in zero order, the zero order number is going to be the zero exponent up here next to the concentration of A. And anything raised to a zero power, anything with a zero exponent, is going to be 1. So the concentration of this A raised to the 0 power equals 1. So really we're just dealing with K, the rate constant, times 1, which is the same thing as just plain old K. So right here I have the initial rate equals K for zero order. Now first order means we're going to have a 1 for that exponent, and the rest of the formula stays the same. It's going to be K, the rate constant, K, times the concentration of A to the first power. Now you know anything to the first power is just itself. So the concentration of A raised to the first power is just the concentration of A. That's the same thing. So right down here we have the initial rate is going to equal the rate constant times the concentration of A. Now the second order means that this exponent is going to be 2. We're going to raise this to the second power. So we're going to have the rate constant, which is K, times the concentration of A raised to the second power. The order of operations in math is that you always do the exponent first. So don't multiply K times the concentration of A and then raise it to the second power. Do the concentration of A raised to the second power, and then times it times K, the rate constant. So we have down here the initial rate equals K, and this is just a different way to write K. The concentration of A to the second power is the same thing as the concentration of A times the concentration of A. It's the same thing. Now these down here in the first and second order, I have the problems rearranged, but this is the same thing that we were just talking about. I just rearranged the formula in case we need to solve for K, so we can get K isolated on one side of the equal sign and get everything else on the other side. But this and this are the same formulas. They're just rearranged a little bit so they're easier to work with. Same for the second order. This is the same thing as this. They're just rearranged in a different way, but the answers are going to be the same. Now, if we're thinking about rate, just rate in general, we can think of it as the change, which is this little triangle here. That means change. Change is just the final number of something minus the initial number of something. So say you're sitting in your house and you're going to drive to your friend's house, which is 60 miles away. So you drive for 60 miles to your friend's house. So after you get finished driving to your friend's house, you've driven a total of 60 miles, and that's the final. And then you want to minus the initial, which is 0 miles, because you were at your house. So you started at 0 miles, and you ended up 60 miles away. So that's going to give you 60 miles total. And when you left initially at 2 p.m., and you got there, the final time was 3 p.m. So you do the final minus initial, and that's going to equal 1 hour. So now you have 60 miles over 1 hour. And so that's going to be your rate, or your speed. Speed is just a subcategory of rate. So this is your distance over time. And so a rate is the change of something on the top of the fraction over the change in time. So rate is always going to have time included into it on the bottom. Now, this is just the general formula for rate. And so we have here the change, which is this triangle again, final minus initial, the change in the concentration of A, and A would be oxygen or carbon dioxide or any kind of chemical that we're working with as a reactant, over the change, the little triangle, in time. Also, the rate law that I was just talking about is the rate equals K, this rate constant, times the concentration of A to the power of whatever order we've figured out. So if these are both correct, this is correct and this is correct also for rate. If those are both correct, we can set them equal to each other. And so we have the differential rate law, which is the change in concentration of A over the change in time equals the rate constant times concentration of A to the power of the order. And that's what this N is. It's just whatever the order is, 0, 1, or 2. Now that we've refreshed on the differential rate law, we can go back to our 0, first, and second order, and we can incorporate that into what we've learned. See, here is the change in concentration over the change in time, and here is the rate equals K. This is for the 0 order. So this would be the differential rate law for the 0 order. And here is the change in concentration over the change in time. And this is the first order formula for the rate. The rate constant times the change in, or times the concentration of A. So we set those equal to each other. So this would be the differential rate law for the first order. And then the same thing over here. So this would be, of course, the change in concentration of A over the change in time, set equal to the second order rate law, which is the rate constant times the concentration of A squared. Now if we rearrange that, here's the zero order formula, differential rate law formula. And if we rearrange that, because calculus, and I'm not going to get into the calculus of how to rearrange this, you'll just have to trust me, or you can look it up somewhere else. Using calculus, you can rearrange this zero order differential rate law into this integrated rate law. So this would be the integrated rate law for zero order. Same goes for the first order. We can rearrange this differential rate law formula for the first order, and because of calculus, we end up with this purple formula down here, which is the integrated rate law for the first order. Same thing for the second order. We rearrange this using calculus, and we end up with this formula for the integrated rate law for the second order. So now we need to keep these purple formulas in mind when we go to do these practice problems. So here's the first problem. The rate of a reaction is quadrupled when the concentration of one reactant is doubled. What is the order of the reaction with respect to this reactant? Now remember, the reactant is one of the ingredients. When you're baking a cake, the flour, the sugar, or the eggs would be the reactants, and the cake would be the product. So the reactant is going to be on the left side of the yield arrow. So A in this case would be a reactant. So even if it's plus B, even if we have other reactants in there, we're just dealing with one reactant right now in this question. So it says the rate of a reaction is quadrupled when the concentration of one reactant is doubled. So let's go back and read this again. The rate of a reaction, the rate is quadrupled when the concentration of one reactant is doubled. What is the order of reaction with respect to this reactant? So if the rate of a reaction, and remember it's going to be rate, and sometimes you'll see a little lowercase I down there for initial rate, but it doesn't have to be, it can just be plain old rate. When the rate of a reaction is quadrupled, when the concentration of a reactant is doubled. So remember, these brackets mean concentration, and this A would be the reactant. So the concentration is doubled, it's times 2. But the rate of the reaction, it said, is quadrupled, so that's times 4. So if you bring these numbers down and you go 2 and you put the rate on the right side equals 4, what exponent next to the 2 should there be to make this equation correct? So this exponent should be a 2, because 2 to the second power equals 4. So if this exponent is 2, that would mean that this is a second order reaction. Now, if we're working with a second order reaction, and we're dealing with the reactant, and we're just going to call it A, then that means the rate law for this is going to be rate equals the rate constant K times the concentration of A raised to the second power, because it's in the second order, so the exponent is going to be 2. Now remember, the differential rate law is going to be the change in the concentration of A over the change in time set equal to the rate constant times the concentration of A to the second power. So this is going to be what we need to keep in mind in case we get asked any more questions about this specific reaction. Now also, since this is second order, we can also rearrange this through calculus in order to get the graphing equation for it, in order to get the integrated rate law for it. And what did we do? This is second order, and here in purple down here is rearranged. So it's going to be 1 over the concentration of A at the time, which is kind of the same thing as saying A at the end of the reaction, final. I'm writing F for final, but usually you'll see it in T for time, equals the rate constant times the entire time it takes plus 1 over the concentration of A originally. That O down there is for originally, the original concentration of A. So let's write that down also. For second order, now remember this is for second order reactions. 1 over the concentration of A T, and that's final, or you can write an F for final, the final time, at the final time. This just means whatever the concentration is at the end. The concentration after the reaction. And that's equal to K, the rate constant, times T, the time it took, plus 1 over the concentration of A originally. Now, do not get this confused with the 0 exponent for 0 order. That's totally different. This means the original concentration. That's why it has the O at the end of it in the subscript. So 1 over the concentration of AT equals KT plus 1 over the original concentration of A. And that's for second order, just for this reaction in this problem. Now, a reaction in the form of A to products is second order. Now remember, we were just dealing with second order, so we should know what we're talking about a little bit. A reaction in the form of A to products is second order with a rate constant. Now what does rate constant stand for? The rate constant is that lowercase k that's in the formula. So the rate constant of 0.225 liters per mole times seconds. So K equals 0.225 liters per mole times seconds. If the initial concentration of A is 0.293 moles per liter, now remember this says initial concentration of A. or initial, or as I was saying earlier, original. So that would be bracket A with the O down at the bottom, the original. So the original or initial concentration of A is 0.293 moles per liter. And we got that from this information right here. Now the question is asking, what is the molar concentration of A after 35.4 seconds? So 35.4 seconds would be the time, T for time. So remember the second order formula that we wrote is 1 over the concentration of A at the end of the time equals KT plus 1 over the original concentration of A. So that means if we plug in these numbers, we're going to be 1 over the concentration of A after 35.4 seconds equals, and K is up here, remember, so equals 0.225 liters per mole times seconds times the time, which is 35.4 seconds, plus 1 over the original concentration of A, so that's going to be 0.293 moles per liter. So let's figure this out. First, we're going to multiply these two together, and this is time, says 35.4 seconds. So we can cross this seconds out because it cancels out with this seconds on the bottom of this fraction bar right there. So we can cancel those seconds out. So 225 liters per mole times 35.4 equals 7.965 liters per mole, because the only units of measurement left after we canceled out those seconds are liters per mole. Now we're going to add that to 1 over 0.293 moles per liter. So 1 divided by 0.293 is going to be 3.41 moles per liter. Okay, so we want to be able to add that. We want to be able to add the 3.41 moles per liter plus the 7.965, and that's going to give us 11.378. So 1 over the concentration of A at the end of the time equals 11.378. Now, how are we going to turn this 1 over the concentration of A equals 11.378 into just the concentration of A? So what we want to do is multiply both sides by the concentration of A, T, multiply by the concentration of A, T. These cancel each other out, and now we want to divide both sides by the 11.378. So really we're just swapping places with them. So now we have 1 over 11.378 equals the concentration of A at the end of the time. So all we have to do is type into our calculators 1 divided by 11.378, and that gives us 0.0879 moles per liter is going to be the concentration of A at the end of the time. Now for the next problem, for the reaction A plus B plus C yields D plus E. So before we go any further, let's look at this. Which are the reactants and which are the products in this formula? Now remember, if you're baking a cake, the reactants would be the ingredients. It would be the flour and the sugar and the eggs and whatever you put in it. And then the product would be, the finished product would be the cake. So this A plus B plus C, these are all going to be the reactants because they yield D plus E, which are the products. So now let's read this again. For the reaction A plus B plus C yields D plus E, the following data were obtained. And it gives us right here the concentrations of A, B, and C in moles out of liters. And then it also gives us the initial rate. Now remember from the other videos, this is the experiments that I was telling you about that we use to figure out what the order number is for this reaction. So here's experiment 1, here's experiment 2, experiment 3, experiment 4, experiment 5, and experiment 6. So the first thing we need to do is let's look where one of the concentrations is changed while the other ones stay the same, because we only need one reactant's concentration to change while the other reactants stay the same. Because the other reactants are going to be the control in the experiment. So right here under A, and let's see, I'll use purple for A. A stays the same during experiment 4, 5, and 6. It's all 0.20. Oh, it's also 0.20 in experiment 2. So that's where A stays the same. Now B, let's use a different color for B. B stays the same between experiment 1 and 2. It's 0.40. It also stays the same between experiment 3 and 4. That's 0.10. And it stays the same between experiment 5 and 6. That's 0.20. Now C, we'll use light blue for C. C stays the same. Well, it stays the same right here between experiments 3 and 4. It's 0.20. It's also 0.20 up here and 0.20 down in experiment 6. It's also the same 0.4 on experiment 2 and experiment 5. So let's just keep that in our mind in case we need that information. So let's go back to A and see where the concentration of A changes. So the concentration of A changes between experiment 1 and experiment 3. But the concentration of B also changes between experiment 1 and 3. So we can't use that. Now the concentration of A, so let's go back and X this out. Now the concentration of A also changes between 3 and 4. It goes down. It goes from 0.60 to 0.20. And luckily for us, concentration of B stays the same and the concentration of C stays the same. So this is what we're going to use for our concentration of A. So between 0.60 to 0.20, this is cut into thirds. So this is cut into thirds from 0.60 to 0.20 for the concentration of A. And let's look at the initial rate now. The initial rates are 15, and it goes down to 5. So this is also cut into thirds. So between the concentration of A and the initial rate, they both progress at the same pace. So we know this is going to be first order for A. Now I wrote A to the first order up here so we would remember, but now we have to do the same thing for B and for C. So let's find where B is going to change. B is in the middle, and B stays the same between experiments 1 and 2. It changes between 2 and 3, but we need a place where B is going to change, but A and C remain the same. So if we look at A and see where they do not change, but B does, A does not change between these two experiments. It stays at 0.2. C does not change between these two experiments. It stays at 0.2. But B changes from 0.1 to 0.2. So that is doubled. From 0.10 to 0.20, that's doubled. So now let's look at the initial rates on those two experiments. And that goes from 5 to 20. So that is quadrupled. So if B doubles, the concentration of B doubles, while the initial rate quadruples, that means that B is going to be in the second order, because if B doubles and the initial rate quadruples, then we need a 2 exponent right here to make that math work, to make that equation work out. So that means that's second order. Okay, so now I've got up at the top A, the concentration of A with the first order, and the concentration of B with the second order. So now we need to see what order the C is. So here's C right here, the column C. So we need to find a place where C changes between experiments, but A and B remain the same. So B remains the same between the first two experiments, but A does not. A changes. B remains the same between these two experiments, but A does not. A changes. But B remains the same, 0.20, 0.20, and A remains the same, 0.20, 0.20, on these last two experiments here. So we're going to use these under the column of C to find out how the concentration changed. Now it started out at 0.4 and it ended up at 0.2. So that is dividing it by half. Now let's look over at the initial rates of those same two experiments. The initial rates stayed the same. There was no change. So another way to write no change is 0. 0 change, which makes it 0 order. So that means C is going to have a little 0 exponent up here because C is 0 order. So let's put C up here next to the A in the first order, B in the second order, and C is in the 0 order. Now the question says determine the rate law for the reaction. And remember, rate equals K, and then the concentration of A N, and N is whatever order it is. But if we're dealing with more than one reactant, we have to make room for the B and C. So rate equals, the K is still there, times the concentration of A to the first power, because A is the first order, times the concentration of B to the second power, because B is in the second order, times the concentration of C to the 0 power, because C is in the 0 order. Now the next thing that we can do is we can analyze this rate law that we just wrote, because look at this C to the 0 order. What is C to the 0 power? Anything in the world to the 0 power is 1. So C to the 0 power is going to equal 1. So we can just go ahead and cross this out, because this is just the same as saying times 1. And so we don't need that, because 1 times anything is whatever the rest of the stuff is. So we just don't need to include this in the law right now. And now let's look at A. A is to the first power. Well, anything raised to the power of 1 is itself. So we don't need this 1 written up there. It's implied already. So that means the rate law of this reaction is going to be K times the concentration of A times the concentration of B2 to the second power. And if you add these up, 2 plus 1, we have the 1 from the concentration of A that we didn't write down, plus the 2 from the concentration of B, because that's in the second order, equals 3. So the entire reaction, the reaction overall, is the third order. But you don't have to worry about doing stuff in the third order just yet. Just focus on the 0, 1, and 2 order and making sure that you're figuring out these orders individually. Each of these reactants need to be figured out individually of the order, and then you write them all together and multiply them all together, along with the rate constant K. Now, here's our last problem, a chemical reaction that is first order in X. So X would be the reactant. So we would have the concentration of X with a little 1 up there because it's first order. And what's the rate law for first order? Rate equals the K, the rate constant, times A, or in this case X. I'll change that and I'll make that into the X, since that's what specifically what we're working on in this problem. So the rate is going to equal the K constant, the rate constant K, times the concentration of X. And you notice I didn't put the little 1 up there just because it's implied. It's an invisible 1. So let's go back to the question. A chemical reaction that is first order in X is observed to have a rate constant of 1.2 times 10 to the negative 2 per second. So what's a rate constant? The rate constant is the K. So the K is going to equal 1.2 times 10 to the negative 2 per second. So if we write this out, if we write this entire rate law out, we would be writing rate equals 1.2 times 10 to the negative 2 per second times, brackets, times the concentration of X. Now let's read on with the question. If the initial concentration of X is 2 molarity, so that means the initial concentration of X, or as I say, original, so I put a little O down there, is 2.0 molarity, or moles per liter. What is the concentration of X after 200 seconds? So the time would be 200 seconds. And what we're looking for is the concentration of X after the time is over. So I'm going to put a question mark there. So if you remember the integrated rate law for the first order is the natural log of the concentration of A at the end of the time equals negative KT, the natural log of the original concentration of A. So let's write that down. Okay, so this is the first order integrated rate law that we're going to need to plug in all these numbers and calculate out. So let's write this down, plugging in the numbers. So we have the natural log of the concentration of A at the end of time, or X in this case. We're talking about X at the end of time, at the end of the time. And that's what we need to figure out, equals negative K, and K equals 1.2 times 10 to the negative 2 per second, times the time it took, which is 200 seconds, plus the natural log of the original concentration of X, which is 2 molarity. Now, first of all, we can cancel some stuff out. This S this S underneath the K can cancel out with this S in the time before we multiply these together. So now let's multiply negative 1.2 times 10 to the negative 2 times 200, and that's going to equal negative 2.4. So all of this right here is negative 2.4. Now we need to take the natural log of 2. So on your calculator, find the button that says LN. It's usually next to your log button. Click LN and it'll open up a parentheses for you. Punch in the number 2 and hit enter. So the answer is 0.693. So this natural log of 2 is 0.693. Now we need to add these together. Let's add these together. So 0.693 plus a negative 2.4 equals a negative 1.707. So we have, and I'm going to write this at the top of the page, the natural log of X at the end of the time is equal to negative 1.707. Now, how do we figure out the natural log of x to the negative 1.707? How do we figure out what x is? How do we get rid of that natural log we have up here? So the opposite of the natural log on your calculator is actually another little button with a lowercase e and an exponent box next to it. So these are going to figure each other out. So this is called the base 10. And I have more videos in my Chemistry 1 playlist about logarithmic functions and natural logs and the whole inner workings of those in case you're interested. But for right now, all you need to know is if you want to get rid of a natural log, you have to use the E exponent key on your calculator. And all you do is you just punch in the E, and then it gives you a little spot to put in the exponent you want. And the exponent we want to use is this answer that we have right here, this negative 1.707. And if you punch in e to the negative 1.707, you are going to get 0.1814. And that's it. So 0.1814 equals X. And that is the concentration which is the same thing in this case as molarity of the reactant that we are calling X. So I hope this helped. Please feel free to leave comments below and like and subscribe.